Hi, hello, welcome back. So, for today, we will be starting with our BJT AC analysis. Okay, so this will be our fourth lecture for midterms. Okay, last time we have discussed DC analysis. So in the DC analysis, we usually solve for the DC parameters and so DC parameters such as DC currents and DC voltages. So what are those? So you have the emitter current, you have the base current, you have the collector current, and then you have the voltages such as your VCE, VBC, VCVE, and VB. Okay, so what is the importance of the DC analysis? So in the DC analysis, we are establishing where is your Q point operating. So where is your Q point located? So what is the importance of that? So the location of your Q point specifies what is the function of your amplifier. So if your Q point is located at the active region, therefore your transistor is operating as an amplifier, while when your Q point is located between the saturation and the cutoff and vice versa, your transistor is operating as either a switch or as an inverter. Okay? So in DC analysis, we are separating your AC signal from your DC source. Okay, so we are assuming that during DC, your capacitors uh, that are connecting your input signal and your output signal to your amplifier circuit is open. So since the capacitors are open, therefore we are separating, or we are disconnecting your AC source from your circuit. So in AC analysis, however, we are going to try to analyze your circuit by using your AC signal only. So in this case, what are we going to eliminate? So we are going to assume that your capacitors are already turned on while your DC sources must be removed. Okay, so how do you remove DC source? How do you kill your DC source? We usually short it. Okay, so to start with, we have here to begin the analysis of small signal AC response of BJT amplifier. The knowledge of modeling the transistor is important. So what do we mean by um, So what do we mean by modeling the transistor is important? So we will be discussing here two models. We have the RE model and we have the hybrid equivalent model. So although they are the same, we will find out later that they are really related to each other, and we can see their similarities. Okay? So if we know the RE model, we can easily understand the hybrid model. Okay? So the input signal will determine whether it is small signal or large signal analysis. So how do we determine whether this is a small signal or a large signal? So ma'am, is 1 millivolt considered as a small signal? Is 1 volt considered as a large signal? Actually, class, it is not on the numerical quantity which will determine whether your amplifier is a small signal AC amplifier or a large signal AC amplifier. So technically, it will be dependent on, again, your active region. Okay, so for example, you have here your active region. So if we have a point here, so if we input or we place an AC input that is just right enough so that your output will not shift your Q point very far from your active region. So we have a small signal analysis. Usually, class, small signal analysis is free from distortion. Okay, so large signal analysis is a different story. So large signal analysis is also what we call power amplifiers. So power amplifiers will be discussed after electronics 1. So for this time, we're going to focus on small signal. So we're going to make use of an input signal that will just maintain your cue point within this active region. And we're going to make sure that your output is free from distortion. So what do we mean by free from distortion? Your output will just like look like your input, okay, just have a higher or an amplified value. But what your output waveform is, it will just look like your input signal. So it is free from distortion. So large signal analysis is somewhat your output is already distorted. Okay? So the goal when modeling small signal behavior is to make of a transistor that work for small signal enough to keep things linear. So when you say nonlinear, so that means we are not going to distort your signal too much. So if we can see distortions, if we can see clippings, therefore we are no longer at the small signal analysis. Okay? So there are two models commonly used in the small signal analysis. So that is the RE model and we have the hybrid model. So the RE model disadvantages. So this fails to account the output impedance level of a device and feedback effect from output to input. While hybrid equivalent model, this is limited to specified operating condition in order to obtain an accurate result. So usually in the RE model, um, we usually make use of several computations, okay? While hybrid equivalent model, those computed value is already given through the specification sheets of the transistor. But anyway, we will be dealing with that as we go on with our discussion. So how does the amplification be done? Okay, so you might be wondering why your output is will be greater. How is it possible for your output to be greater than your input signal? So we know that when about the conservation of energy, the output power of a system cannot be larger than in its put. So where will be the larger value come from? Usually, in this case, the output is usually smaller than the input because of several losses that might occur during the process. Okay, so how does the amplification be done? When in fact, without considering the losses, okay, so the highest efficiency that is possible is only 100%. So what do we mean by 100%? Your output will be equal to the input considering no losses. But losses is always present in any system. Okay? So how is amplification possible then? So the input DC plays the important role for the amplification. So although your DC source is not the one which is being amplified. So the one which is being amplified is your AC source actually, but your DC plays an important role for the amplification because it contributes to the level of your AC domain. Okay, so where the conversion will become POAC divided by your P in DC. Okay, so simply speaking, so we will be placing here a control mechanism. So this is your input signal and this is your DC input signal. So usually the output is must be equal to your AC signal. So a portion of your DC signal will be transferred or will be contributed with to your AC signal so that your AC signal will be of a higher value compared to its original input value. Okay, so the how are we going to separate your AC from DC analysis? So from considering the DC analysis yet, we said that your capacitors in DC are said to be open, so no problem. So when this is open, that separates your AC signal here and your AC output signal here. However, what we want to consider now is your AC signal here. So what we are trying to eliminate now is the DC source, which is your VCC. So we are trying to make your DC supply to zero potential. So how are you going to to remove your DC supply, how are you going to kill your DC source? So we're going to make this zero potential. So what do we mean by zero potential? That means we are just going to ground your sources. So all DC sources will be grounded, or will be um will be made equivalent to a zero voltage. Okay? So your input coupling capacitor, this is no longer open. So we have to replace this with a short circuit. Okay? So with large value. So it will block your DC. All of the DC components will be blocked, and it allows, or it passes your AC signal. So your bypass capacitor, so we have here a bypass capacitor. Later we will be discussing what is the importance of this bypass capacitor. So the bypass capacitor will likewise be short circuit. So it has large value during AC condition. And then your output coupling capacitor will be again turned to short circuit, okay, which blocks your DC and let your AC signal passes. So for our voltage configuration, voltage divider configuration under AC analysis, it will look like this. Okay, so your DC supply is made zero potential, so we ground it. Your input coupling capacitor is turned into short circuit. Your output coupling capacitor is turned to short circuit. So what is interesting here is the effect of the short circuit bypass capacitor here. So when this is made short circuit, what happens is it bypasses the effect of your RE. So what do we mean by that? Any resistors placed in parallel with a short circuit makes the value of your resistor equal to 0. So therefore, at the redrawn circuit here, RE is no longer present. Okay? So you might be wondering, if we wanted RE not to appear during AC analysis, why place RE in the first place? Okay? So fixed bias configuration, it doesn't have RE. So therefore, we don't need to use bypass capacitor in fixed bias configuration. However, we have established the fact in your DC analysis that RE plays a very important role in the stabilization, okay, in the stability of your circuit. RE helps to make your circuit stable, and that is on the DC portion. However, we'll find out later that RE is not very, very helpful when it comes to the amplification. That's why we place a bypass capacitor here. So this bypass capacitor here is open during DC, permitting the effect of RE during DC condition. While this is being shorted at AC condition, removing now or bypassing the effect of your RE. So this is a win-win situation. RE is needed at the DC analysis, and it is not needed during AC analysis. So what do? We place a bypass capacitor here. So during AC analysis now, look, the effect of RE was removed. Okay? So this is the redrawn voltage divider configuration after removing your DC supply and insert the short circuits for the capacitors. Okay? So from this one, we are going to model. Okay? We're going to model your transistor here. So this is now your transistor small signal AC equivalent circuit. This is your base, which is connected to the parallel combination of your R1 and your R2, and then this is your collector, and then this is your emitter. So this is the redrawn equivalent circuit for AC analysis. So your modeling begins here. Depends on what type of model we're going to use. As mentioned earlier, we have two types of models. You have the RE model and you have the hybrid model. So depending on what we're going to make use, we will be replacing your transistor here. Instead of using this one, we will be using the transistor model here. Okay, so AC bias analysis starts with redrawing your circuit. So by first, kill all DC sources. So some of the circuits, they only have one DC source. Majority of the circuits, they have one DC source. But we have discussed two circuits having more than one DC source. So if you can still remember, you have the split supply and you have the common base configuration. So in the common base configuration, you have VEE and you have VCC. So in the split supply, you have the VCC also and you have the VEE. So in those cases, all of the DC sources, we have to kill them. Okay, so how do you kill them? So just uh just replace them with short circuit or replace them with a ground. And then your coupling, we have two coupling capacitors, one at the input and one at the output. And you have one bypass capacitor. Okay, so coupling and bypass capacitors are replaced by short circuit equivalent. So the effect of these capacitors is to set the lower cutoff frequency of the circuit. So at the meantime, we'll just have to accept this fact that this capacitor here is just open for DC and shorted for AC. But in electronics too, we will see that there is more to this capacitor. Okay, so this will set up the lower cutoff frequency for the circuit. Okay, so this is up to now. So we will be discussing that lower cutoff frequency at electronics too. So we're going to inspect the circuit. We're going to replace your BJT with its small signal model. So there are two models. You have the RE or the hybrid model. Okay? And then solve for the voltage and current transfer functions, and you have the input and output impedances. So the good news here, class, is for AC analysis, we are going to consider only four parameters. Okay, so unlike for DC, you have three currents, you have several voltages to solve for. So in AC analysis, usually we only have four important parameters to consider. So what are those four important parameters? You have the voltage gain. Okay, so we have the voltage gain, you have the current gain, okay, you have the input impedance. Some other books they use RI, some other books they use ZI. So that is the input impedance, and then we have the output impedance. Some other books they make use of RO. So for the duration of our discussion, so we will be discussing how to get these four parameters. Okay, in dealing with your AC signal analysis. So solve for voltage. So the voltage transfer function, that is your voltage gain, the current transfer function, that is your current gain, and then your input and your output impedances. Okay, so four important parameters. Okay, so these are the four important parameters. We have a two-port system. So we have the input impedance ZI, you have the output impedance ZO, you have the voltage gain, and you have the current gain. Okay, so input impedance, usually they ranges from a few ohms to mega ohms. Okay, so the input impedance of an amplifier is the value of a load when connecting a single source to the input terminal of the amplifier. Okay, so for a two-port system, how do we determine your input impedance? So you might be wondering, if we can simply get an ohmmeter and then measure the resistance at the input side of your two-port system. So actually, input impedance, class, cannot be measured using an ohmmeter. So usually, the ohmmeter that we are using at the laboratory used to measure DC resistances. Okay? So the input impedance that we are talking about here is AC. So therefore, it cannot be measured using your ohmmeter. So the input impedance of a transistor can be approximately determined using DC biasing because it doesn't simply change when the magnitude of the applied AC signal is changed. Okay? So we are going to make use of a sensing resistor here. So we call this R sense. Okay? And then we can solve for I input here. So your I input is simply Ohm's law. So you have Vs minus VI. So the VI here is the one which is being amplified. So this is your source and this is your VI. So VI is the one which will enter your transistor circuit. VI is the one which will be amplified at your transistor amplifier circuit and not VS. Okay, VS is your source. So in the laboratory, this is your signal generator. So when you set your signal generator to, for example, 5 millivolts, not all the 5 millivolts will be amplified. Why? Because there will be a drop here at the sensing resistor. So only your VI will be amplified and not your VS. Okay? So solving for your I input. So I input is VS minus VI divided by your R sense. So your ZI is equivalent to VI divided by II. Okay, so you can measure this using your AC voltmeter or using your oscilloscope. So it can either be yeah, peak to peak, or it can be peak voltage, or it can be RMS value. Okay, so depending on what AC parameters you are using. But usually, if you're using the oscilloscope, we can see the peak value or the peak to peak value of your input. Okay, so you can determine. So all of these parameters here are AC. So they are not your usual DC currents and voltages that you are measuring using your DC voltmeters or your DC ammeters. Okay, so demonstrating the impact of ZI, usually ideal source, ideally speaking, when you have a voltage source, you have is resistance in series. So ideally, your source is equal to 0. So when your R source or your R sensing is equal to 0, all of your 10 volts here will be equivalent to your, or will be seen to your VI. So therefore, all of the 10 millivolts will be amplified because the one which is amplified is your VI here. However, with source impedance, let us say 600, and your input impedance, which is 1.2 kilo ohms, solving for VI using voltage divider, since VI is in parallel with your ZI, using voltage divider configuration, you have ZI multiplied by VS all over ZI plus R source. So solving for that, that will give you 6.6 millivolts. So from the 10 millivolts here, only 6.6 millivolts will be amplified by your transistor amplifier circuit. Okay, how about the 3.4 volt, the 3.4 millivolts? So the 3.4 millivolts was dropped here. Okay, so that is already considered as a loss in the system. So that is the impact of ZI. If you will be using a ZI which is very, very small, which is smaller than 600, what will happen? So for example, we interchange the value. 600 is your ZI and your R source is 1.2. So only 3.4 millivolts will be amplified. So therefore, if you have an amplifier having a gain of 10, so that will only be 3.4 millivolts multiplied by 10. Okay, but if we have a greater ZI, that will be 6.6 millivolts multiplied by 10. So that is the impact of your ZI. That means we have to choose an input impedance that is greater than your source resistance so that it will have a greater share of your VS. Because if it has a lower share of your VS, the one which will be amplified here is very, very small. Okay, so for the system of the figure below, we're going to determine the level of your input impedance. Okay, so how are we going to solve for this class? So we have here your solving for I input. So I input is Vs minus Vi divided by R sense. So that will give you 0.8 microamperes. Okay, and then solving for Zi, Zi is 1.2 millivolts. This one given your Vi divided by the solved I input, which is 0.8 microamperes. So that will give you 1.5 kilo ohms. Okay? Take note, take note class that Zi is not being measured using your normal ohmmeter because Zi is an AC parameter. Okay? So this is an AC parameter. And usually your ohm meter is used to measure DC resistance only. So that is the first parameter. The second parameter is the output impedance, ZO. Okay, so usually this ranges from few ohms to 2 mega ohms. So the output impedance of an amplifier is determined at the output terminals looking back into the system with the applied signal set to 0. Okay, so we are going to make your VS equal to 0. Okay, so we are just looking at the output terminal of your two-port systems. So we have here I/O. We placed a sensing resistor at the output. So we have here your V. Okay. So I/O is given by V minus your VO here. So this is the output voltage. So divided by your R sense resistance. Okay. So by knowing your I/O, we can solve for ZO. ZO is VO all over I/O. Actually, this is just Ohm's law. Okay. We don't have a new formula here for electronics. We will just be using your Ohm's law formula here. So even at the input impedance, we just make use of Ohm's law. So ZO is equivalent to VO divided by IO. Okay? So if you have an amplifier and we place a load resistance here, when your RO is very very large, so the current coming from an amplifier, it will be divided by 2. So one will be flowing across your output impedance and the other will be flowing across your load resistance. So usually your load is your speaker. So if this is an amplifier, usually what load are we talking about here? We're talking about your speaker. Okay, so our main goal, so for RO, which is much greater than RL. So if this is very very high, majority of the current wants to flow across the load instead of your uh, output impedance. Okay, so the current always chooses the lower resistance path. So therefore, IL is greater than your IRO. So we wanted RO to be greater than your load so that majority of the current will be flowing across your load resistance. Okay, so when this is very very large, when very very small current flows here, so your ZO is much greater than or equal to RL, so ZO becomes an open circuit. So for the system of the figure below, determine the level of the output impedance. So we have here solving for IO. So this is just an introduction class. So this is just direct substitution. So we have here IO 16 microamperes solving for ZO. So that will give you 42.5 kilo ohms. Okay. So for the system of the figure, let us determine the value of ZO. If V is equal to 600 millivolts, R source is equal to 10 kilo ohms, and IO is equal to 10 microamperes. Okay, so what we're going to do here, since we are given IO, we can solve for VO. Okay, so VO is equivalent to V minus IO multiplied by the R sensing resistance. So VO is equivalent to 50 millivolts. And using the value of VO and the value of IO, we can determine ZO. So ZO is equivalent to 50 kilo ohms. Okay? So using the ZO obtained in the previous example, which is 50 kilo ohms, what is the current flowing across the load here, IL? So if your I amplifier is 6 milliamperes, so we will be using current divider formula. Okay, so since we are using RL here, we will be, so current divider rule, your IL is your ZO from the amplifier, opposite, divided by ZO plus RL multiplied by the total current, which is your I amplifier. So from the previous example, we have solved for ZO, which is equal to 50 kilo ohms multiplied by the total current, which is 6 milliamperes, divide by 50K plus 2.2 kilo ohms load resistance. So that will give you 5.747 milliamperes. So is this a good value? Yes, this is a good value because majority of the current flows across your load and not at your output impedance. So why is the load important? Because this is your speaker. So for your speaker to sound properly, for your speaker to sound nice, proper current must be flowing across it. So therefore, our main goal is to have the majority of the current from the amplified current to flow across your load and not your output impedance. So that is the impact of the output impedance. Okay, so we have the voltage gain and we have the input impedance and the output impedance. Okay, so the next is the voltage gain. So the voltage gain has a symbol of AV. Okay, so DC biasing operate the transistor as an amplifier. So amplifier is a system that having the gain behavior. So what do we mean by the gain behavior? So your output must be greater than your input. So it is said to have a gain. So the opposite of a gain is an attenuator, or it attenuates. So attenuator is when your output is lower than your input. Okay, so the amplifier can amplify as current, so that is current amplifier. It can amplify voltage, so you have a voltage amplifier, or it can amplify power, so it is a power amplifier. So for a voltage gain, it is said to have AV, so the symbol for gain is A. Okay, other books they use G as a symbol. Okay, so AV for the voltage gain, AI for current gain. So some use AP. So AP is for power gain. Okay? So usually it is the ratio of the circuit's output to the circuit's input. So AV, ratio of the circuit's output versus circuit's input. So we have AV. So this is the ratio of the output voltage versus the input voltage. Current gain. So what is current gain? It is the ratio of the output current all over the input current. And what is your power gain? So power gain is the ratio of your output power versus your input power. So this is the ratio of the output versus the input. So for us to have a gain, the value here must be greater than 1. So when you have a greater than 1 value, that means your output is greater than your input. So therefore, you have a gain. You have an amplifier. Okay? So the small signal AC voltage gain can be determined by this one. So VO all over VI, output voltage. Usually the gain is a unitless parameter. Okay, so going back here, so this is VI all over I input. So this is VO all over I output. So voltage over current, so this is in terms of ohms. This is also is in terms of ohms. Okay, however, for voltage gain, so this is volts, this is also volts. So volts will be cancelled out. So usually, gain is a unitless parameter. So it has no unit. Okay? So by referring to the network below, the analysis are, if you have no load here, you have no RL, so this is just an open circuit. So you just measure the output voltage and this is your input voltage. So voltage gain at no load, okay? So voltage gain at no load when in your RL is infinite or open circuit. So this is simply VO all over VI. Okay, so if we have a source resistance here, we will not be calling this AVNL anymore. So we will be calling this as your AVS. Why? Because we are comparing the gain, the increase in VO with respect not to VI, but with respect to VS. So how do we solve for that? So in this case, okay, so in this case, class, we will be solving first for VI. So by voltage divider principle, okay, so what is VI? VI is directly connected parallel to ZI. So therefore, VI is equal to ZI multiplied by your VS all over ZI plus RS, or the sensing resistor. Okay? So if we will be getting the gain, so what will be the gain here? Your VI, if you're going to bring down your VS here, okay, so your VI will serve as the first output while your Vs will serve as your input. So this is equivalent to just bring that down here. So that will give you Zi all over Zi plus Rs. So this is your Vi all over Vs. Okay, so with source resistance now, that is from Vo to Vs. So to get your gain there, so that will give you, class Vi all over Vs multiplied by Vo all over Vi. Okay? So as you can see, Vi will be cancelled out. So that will give you Vo all over Vs. So this is your AVs. So the difference between AV and L is this is simply VO all over Vs, not starting with the source voltage. Okay? So what is VO all over, what is AVs? AVs is Vi all over Vs times Vo all over Vi. Okay? But what is Vi all over Vs? Vi all over Vs is Zi all over Zi plus Rs. What is Vo all over Vi? Vo over Vi is equal to AV and L. So therefore, your AVS is equal to Zi all over Zi plus Rs multiplied by the no load voltage gain. So what is the importance of this class? Because the no load voltage gain is usually the one which is given in the specification of your amplifier. Okay, because when your transistor is being manufactured, they do not know what will the user use as a load. So it doesn't know where are you going to make use of that amplifier circuit or of that transistor. So we don't know the gain yet. So if you already know the the purpose of your transistor or the application of your transistor, so therefore you will be placing a load. Okay, so usually the no load voltage gain is given. Okay, so you have here the no load voltage and the source, the voltage gain when you have a source resistance. Okay, so VO all over VI, this is VO all over VI, AVS is VO all over VS. Okay, so for BJT amplifier of the figure, let us determine VI. Let us determine I input, ZI. So this is a very simple example class. So this is just a formula. Okay, so we'll just familiarize ourselves with the with the different parameters. Okay, that we will be encountering once we discuss the AC side, different configurations. So for AV and L, so we are given AV and L. So since why do we use AV and L? Because we have no load here. Okay, so AV and L is VO all over VI. So VO is 7 point. So we can solve for VI. So given the AV no load gain, so we can solve for VI. VI is VO 7.68 volts from here divided by the no load voltage gain, which is 320. So that will give you 24 millivolts. So there is an amplification, right? Because if your input is 24 millivolts, when you measure your output, it became 7.68. So the amplification states that from 24 millivolts, it increased or it was amplified up to 7.68. So it was increased or amplified 320 times. So that's what you mean by amplification. Okay, so using your formula then, using your I input. So I input is Vs minus Vi. So you use the Vi that we have solved here earlier divided by Rs. So that is 13.33 microamperes. Okay, so using 13.33 microamperes, we can solve for Zi. Zi is 24 millivolts divided by 13.33 microamperes. So that will give you 1.8 kilo ohms. Okay, so how do we solve for AVS? We will just be using the formula. So the formula is Zi all over Zi plus Rs multiplied by AVL or no load voltage gain. Look at the voltage gain class. It lowers down. Why? Because we are determining the increase from here to here. So not all the 40 millivolts was amplified 320 times. Why? Because some of the some of the voltage from 40 millivolts was dissipated by your RS here. Okay, was dropped, was became a loss at your RS here. So therefore, your gain here becomes lower. Okay, the one which has the highest gain is always the no load voltage gain. So we will be discussing more of the voltage gain as we go on with our discussion. Okay, so in this case, you just familiarize yourselves with the formula. Anyway, no new formula. Everything was derived. Everything this came from voltage divider configuration. So this is Ohm's law. This is Ohm's law, series circuit, so everything. So the new here is just the voltage gain, which is output all over input. Okay, so for the current gain, we cannot say that no load current gain. So for the current gain, there is always a load. Okay, because if this is open, that means no output current will be flowing. So therefore, we have to have, or we have to place a load in determining the current gain. So there is no such thing as no load current gain, because if there is no load here, it is an open circuit. So if it is an open circuit, therefore no output current is flowing across your circuit. Okay? So determining the loaded current gain. Current gain is the output current divided by the input current. So how do you solve for I/O? By just looking at this figure. I/O here is, okay, negative VO all over RL. So why do we have a negative sign? So why do we need a negative sign? Because your I input is going here and your I output is going here. So look at their direction. They are opposing. So when your two currents are opposing, that means we have a negative sign here. Okay? So why in the voltage gain we don't have any negative sign? Because your input is plus minus, your output is plus minus, so they are the same, so therefore no negative sign. But in the current, we have a negative sign because your input is going here and your output is going here, so they are opposing, they are not of the same direction. That's why we place a negative sign here. Okay, so what is IO? IO is VO divided by RL. What is I input? I input is VI divided by Zi. Okay? So we have here VO all over Vi multiplied by VO Zi, getting the reciprocal. So we have here VO Zi VIRL. Okay. So what is VO all over Vi? So VO all over Vi is AV and N. Okay? So we have here, why no NL? Why didn't we place NL? Because it is already loaded. Okay, so it's loaded. So the loaded voltage gain, AI is equivalent to the loaded voltage gain multiplied by Zi all over Ri. Okay, so Zi is ohms, RL is ohms, so it will be cancelled out. Voltage gain has no unit because volts will be cancelled out. Therefore, just like voltage gain, current gain is a non-unit parameter. So it is a parameter with no unit. Okay? So voltage gain multiplied by Zi all over RL. Now, we have seen or we have witnessed a negative sign. So what do we mean by the negative sign there, class? So IO is negative VO all over RL. Okay, so the negative sign there shows the phase relationship. So the phase relationship between input and output sinusoidal signal is important for a variety of practical reasons. Fortunately, however, for a typical transistor amplifier at frequencies that permit ignoring the effect of the reactive elements, the input and the output signals are either 180 degrees out of phase or in phase. Now, just like what we have seen earlier in the voltage gain class. So when your voltage gain is positive, okay, when your gain is positive, that means it is in phase. So what do we mean by that? If this is your input, your output is amplified, but it has the same phase. So if this is positive half cycle, this is also a positive half cycle. If this is negative half cycle, this is also negative half cycle. Okay? But if you see a negative sign, just like what we have seen in the current gain situation, so if you see a negative sign, it is said to be 180 degrees out of phase. So the sign is very important, okay? Because the sign will tell you whether your input and output are in phase or out of phase. So what do we mean by 180 degrees out of phase? If this is your input, your output will look like this. So they are 180 degrees out of phase. So when your input is positive half, your output is at the negative half. When your input is at the negative half, your output is at the positive half. Okay? So that is what you mean by 180 degrees out of phase. So all of this, we will be discussing this one by one, and we're going to integrate this with the DC circuits that we have discussed. Okay? So when we have fixed bias configuration, how do we get the input impedance, the output impedance, the voltage gain, the current gain for a fixed bias, for a voltage divider, for an emitter stabilized, for a DC feedback circuit? Okay? So how do we get the four important parameters for a common base configuration? How do we get the four parameters for a common collector or the emitter follower configuration? So we will be discussing those in our next video. Okay, so for this video, we just had an introduction with the AC analysis. So just for a recap, in the AC analysis, we will be turning off. You will be shorting all your DC sources. So all the only input that we're going to consider here is the AC input. Okay, so after doing that, we're going to assume. Okay, we're going to let all your capacitors be short circuit, equivalent to a short circuit, and then we're going to compute for the four important parameters. So for AC analysis, we will just try to evaluate all of these four: the input impedance, the output impedance, the voltage gain, and the current gain. Okay, so we will integrate those to our DC. We will be analyzing your DC circuits, your DC. How are we going to connect your DC, the things that we have studied in DC, to your AC, if there is a connection between the two. Okay, so all of that will be discussed on the next video. Okay, so have a nice day. Always stay at home. So if you do not have anything to do outside, you just stay at home, and let us pray that everything about COVID here will come to an end. Okay, so have a nice day, and God bless us all. Bye.